Hello everyone and welcome to my channel. This is an educational channel. We look at theories of everything of different varieties and do very deep dives into every aspect of them, and hopefully they'll shed some light on helping you to make your paradigm shift, to adjust to 5D consciousness, to live a more holistic viewpoint, and maybe just satisfy your curiosity. Today we are looking at our 446th video on the reciprocal system of theory from Dewey B. Larson. We're looking at his book called Basic Properties of Matter, which is primarily on chemistry. Larson in the late 1950s was proposed his two fundamental postulates about how he believed the universe behaved. And then through a process of deduction, he deduced the the more detailed properties of the universe, what it would look like if his postulates were correct. And then in books like Basic Properties of Matter, he compares his theoretical universe with the universe that was measured by the scientists and compiled in their scientific tables. Basic properties of matter in this case, such as the melting point and the specific heat and the interatomic distance and the compressibility, all of these have data that describe, this element has this melting point and this element has this melting point. Well, Larson arrived at equations for all of these different things and plugged in all of the elements and compounds and compared his numbers with the numbers that were in the tables. And so we're taking a look at what he came up with. Now, just to give you a quick once-over about what those two fundamental postulates are about and what the reciprocal system is about. It's called the reciprocal system, also known as the universe of motion. It's because Larson, similar to some of his predecessors, believed that the universe was made out of motion, not matter or not energy, but motion. Larson's first postulate states that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. And then the second postulate is more, just kind of nuts and bolts, math and geometry. The universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute and its geometry is Euclidean. So we're going to stay focused on the first postulate and basically saying the universe is made out of motion, and motion is the relationship between space and time. Space and time are reciprocals of one another, therefore. And basically motion is a fraction, with space or time as the numerator and time or space as the denominator. Our most familiar kind of motion is speed or velocity, but in this case speed. And speed is, the bicycle is moving 15 miles per hour. 15 miles of space in 1 hour of time. Space over time. That is the fraction of speed, space over time. So at least for the most elementary kind of motion, it is actually a relationship between space and time. And if you decide to double the speed, you can now say the bicycle is now moving 30 miles per hour. Or equivalently, you can say the bicycle is now moving 15 miles per half hour. That shows a reciprocal relationship between space and time in speed. Now, Larson spreads that out to all of our scientific phenomena, equates them all with motions. Matter is a motion, energy is a motion, pressure is a motion, compressibility, or let's just say acceleration is a motion, force is a motion, electric charge is a motion, magnetic flux is a motion, permeability is a motion. All of these are fractions with space or time as the numerator and time or space as the denominator, with the added part of that postulate that the universe is three-dimensional. So space, time, and motion all come in 3 dimensions. So you can have, for example, matter. Matter is time to the 3rd power over space to the 3rd power. And actually, you can get into areas where you can go up to the 6th power, such as density, because density is pressure over volume. So you have mass over volume. Time to the 3rd power over space to the 3rd power over space to the 3rd power. So density is time to the 3rd power over space to the 6th power. And that helps you identify the units also, and that's part of the discrete unit postulate. Everything is in single units. Everything is quantized. Time and space are quantized. There's a minimum unit of time. There's a minimum unit of space. If you don't have a full unit, and there's a minimum unit of motion, which is 1 unit of space in 1 unit of time. That's our minimum unit of speed. Our minimum unit of energy is time over space. So our minimum unit of energy would be 1 unit of time over 1 unit of space. Now it works out that our unit of space is about 2 millionths of an inch, and our unit of time is approximately 1/6 quadrillionth of a second. So they're very small, but in the case of space, at least, they are large compared to the size of an atom. And if you have 1 unit of space and 1 unit of time, then you have 1 unit of speed, which is also known as the speed of light. And the speed of light is really like the neutral point in this universe. So what we have is a universe of motion. If you're going to accept a universe of motion, you have to accept the idea that motion precedes everything moving. And so motion is the first cause, the first thing. It's the source of everything. If you have nothing in the universe, you still have motion. And what you have is what Larson calls a scalar motion, which is a motion that has a magnitude, but it has no specific direction. A scalar magnitude can be envisioned using a balloon that you put dots on, and with a magic marker or something, and you blow up the balloon, and all the dots are moving away from each other. All the dots are moving in every direction, but they're not moving in any specific direction. So that is a scalar motion, a motion without a specific direction. It's really either out or in. If it's outward, the balloon surface is moving outward. Larson calls that the progression. If the surface is moving inward, Larson calls that gravitation. And if it's moving outward at the speed of light, 1 unit of space and 1 unit of time, that is what Larson calls the progression of the natural reference system. So this is the reference system that nature adheres to. So Larson makes his measurements from this point, this moving reference system, the natural reference system. And then if you have abstractions, if you're making abstractions, basically, if you decide to say that, okay, one of the points on the balloon surface, we will assign that to be motionless. We will assign that to be the reference point. And then when you start measuring those relations in reference to other points on the surface of the balloon, you will be able to measure the directions. And you will, so you basically abstracted the phenomena. That's what Larson would call either the spatial or the temporal reference system. So in the spatial reference system, we have 3 dimensions of space in a still frame, just like what we normally notice here in our world. 3-dimensional space. Space appears to be still. We appear to be moving through it as we move. And so it's, 3-dimensional space background. And then, but time is still moving scalarly. Time is always getting later and later and later. It's always moving forward, the flow of time or the progression of time. And, but it's not moving in any specific direction. So that is a scalar motion in time and a vectorial 3-dimensional still frame background in space. The temporal reference frame is the reciprocal of that, where we have 3 dimensions of time in a still frame, and we have space progressing. Space is always getting farther and farther and farther apart, just like on the surface of an expanding balloon. And but time is still. Now, those are the spatial and temporal reference systems, and they occur in what Larson calls the material and cosmic sectors. The material and cosmic sectors, respectively, are lower than the speed of light or greater than the speed of light. So we've got that speed of light boundary, the unit speed boundary, the null point or the neutral point or the 0 point of this universe of motion is outward in all directions at the speed of light, the progression of the natural reference system. Less than that is the material sector, and greater than that or beyond that is the cosmic sector. In the material sector, we have coordinate space and clock time. In the cosmic sector, we have coordinate time and clock space. And then within these sectors, we also have what's called a time region in the material sector and a space region in the cosmic sector. And that's, again, because of the discrete unit postulate. If you don't have a full unit of space, then you don't have space. So when you have things like atoms and molecules that are interacting in less than 1 unit of space, less than 2 millionths of an inch, then they're not interacting in space because you don't have space. And if you don't have space, then you only have time, because the universe is made out of space-time or motion. And so it's got to be one or the other or both. And so time is where it's occurring. And Larson calls that the time region. This is the inside region of close interactions in the material sector. And reciprocally, in the cosmic sector, this is called the space region, anything that is within 1 unit of time. These are cosmic atoms and cosmic molecules that are interacting in that space because it's less than 1 unit of time. And when you cross those boundaries, again, the rules reverse. Just like when you cross the unit speed boundary, you switched from a spatial reference system to a temporal reference system. When you cross into the time region, the progression and gravitation reverse. So now the progression is moving things closer together, and gravitation is moving things farther apart. And this causes what is called the atomic equilibrium within the time region. The progression is moving things closer together, but it's constant and it's omnipresent and eternal. Gravitation is based on the inverse square law, how close they are together, and that is variable. So where those 2 points reach are the same, where those 2 forces are the same, the force of compression and the force of expansion are the same, that is where the interatomic equilibrium is established. And then also we get our atoms and molecules from rotation. So the progression of the natural reference system is the source. That progression is slowed down in one dimension by a photon, which is a simple harmonic motion or a vibratory motion, a reversing motion that basically is superimposed on the surface of that balloon. And again, that balloon is really, motion is in 3 dimensions. And so it's restricting it in 1 dimension, but it's still propagating it at the speed of light in 2 other dimensions. And so the photon still appears to be moving outward at the speed of light, but it is a start toward reversing the motion of that progression of the natural reference system. And so when it is reversed in 3 dimensions from there, then you have things like atoms and molecules. Okay, so let's start with Larson here in the middle of this chapter number 5 on heat, and that's the title of the chapter, Heat. And I will attempt to address any gaps in that a beginner might be getting from this fairly detailed and advanced treatment here of this subject. Okay, beyond this 3R thermal, now he's determining the specific heat, and in particular he's determining the specific heat is the amount of heat that you need to add to something to raise its temperature by a certain amount. And the gas constant, or R, is the unit of specific heat that he's assigning here, although the gas constant is actually just 2/3 of the unit. And so 3R is the point at which, well, he says beyond this 3R thermal specific heat level, which corresponds to the regional boundary, the region of the time region. So when you get out of the time region by attaining a specific heat level of 3R. And that regional boundary really, I believe it's the melting point, because the solid state is a property of the time region. And then the liquid state is the property of exceeding the time region in 1 dimension. The gaseous state is exceeding the time region in 3 dimensions. So I'm not sure whether he's talking about the melting point or the boiling point, but let's keep going. Again, this is like detective work. You're not going to get all the information at once. You have to kind of piece it together. Most of that is as a result of Larson having to create a whole new language for all this and having to do it all by himself, just about, with no resources. And so he put it out there, but sometimes you have to dig a little bit to extract it. Sometimes you have to dig a lot to extract it. Okay, the thermal motion leaves the time region and undergoes a change, which requires a substantial input of thermal energy to maintain the same temperature, as will be explained later. Now, he's referring to what they call heat of fusion. So, once you get to the melting point, then you also have to add a certain amount of heat then to get across the melting point. Same thing with the boiling point. And that is more substantial with the boiling point, that you have to add this extra amount of heat to kind of cross that boundary. Okay, the condition of minimum energy, the most probable condition, is maintained by avoiding this regional change by whatever means are available. So the atom or molecule is going to do everything it can to avoid this, crossing that boundary, in spite of how much ever heat is pumped into the system. One such expedient, the only one available to molecules in which only one rotational unit is oscillating thermally, is to change from a negative to a positive initial level. So the initial level is always corresponding to the progression of the natural reference system because it is omnipresent and eternal. So the progression outward at the speed of light or in the time region inward is always there, and it always has to be accounted for. So Larson calls this the initial level, where the initial level is plus 2/3 R instead of minus 2/3 R, which it can be plus or minus because of the oscillation of the photon. And so it could be up here or it could be down here. And this is the initial level that's added in before you get started. And then once you start adding temperature, you have to add more if you're down at the bottom of the trough as opposed to up at the top. Okay, the net positive specific heat is 3 2/3 R, where the initial level is plus 2/3 R instead of minus 2/3 R, at the point where the thermal specific heat reaches the 3 R limit. The regional transmission is not required until this higher level is reached. The resulting specific heat curve is shown in figure 3, which I don't have access to here. Inasmuch as but again, it's like many of the other curves, well, this one not yet, but many of the curves that are involved in these are line segments that have inflection points, and you can curve them out, but there are inflection points. There are certain critical points that you arrive at where the rules change or some parameter changes, and so then the slope of the line changes, abruptly. Inasmuch as the magnetic rotation is the basic rotation of the atom, those are the two-dimensional rotations. Every atom has 3 numbers, 2 two-dimensional rotations that alternate, and 1 electric or one-dimensional rotation that is in the opposite direction of the first two. And Larson refers to the two-dimensional ones as magnetic and the one-dimensional one as electric. Inasmuch as the magnetic rotation is the basic rotation of the atom, that electric rotation is optional. It can be 0 in the inert gases or the noble gases, and it can be plus or minus depending on where you are on the periodic table. If you're over there on the, the far right side of the periodic table, then it's negative. If you're on the left-hand side, it's positive. The electropositives are positive. Okay, the maximum number of units that can vibrate thermally is ordinarily determined by the magnetic displacement. Low melting points and certain structural factors impose some other further restrictions. And there are a few elements and a large number of compounds that are confined to the specific heat pattern of figure 3, or some portion of it, where the thermal motion extends to the second magnetic rotational unit, to rotation 2, we may say, using the same terminology that was employed in the interatomic distance discussion. The figure 3 pattern is followed up to the 2 1/3 level. But at that point, the second rotational unit is activated. Now, this is a magnetic unit. Like, so for example, say if you're talking about sulfur, number 16 on the atomic periodic table, its three number in notation in Larson's system is 3, 2, -2. So there's 3 primary two-dimensional rotations, 2 secondary two-dimensional rotations. He's saying when you move to this next, from like there's an initial level and then there's 2 more in addition, like say for that primary magnetic rotation. When you are moved to the next rotation, then that's what he's talking about. So the rules change there. At that point, the second rotational unit is activated. The initial specific heat level for rotation 2 is subject to the same n to the third factor as the thermal specific heat, and it is therefore 1 over n to the third power times 2/3 R equals 1/12 R. So once you get to that point of activating that second unit, you move into the second, into a three-dimensional distribution. Basically, 1 to the third power is 1, but 2 to the third power is 8. So you basically divide by 8. It is 1/8 as effective as it was when you were dealing in the first unit. And so that's 1/12 R. It was 2/3 R. So now if you divide 2/3 by 8, you get 1/12. So it's 1/12 R now. So basically the specific heat is 1/8 of the value that it was before. Like, so for every unit of heat that you're adding, you're only raising the temperature by 1/8 of what you were raising it by before. This change in the negative initial level raises the net positive specific heat corresponding to the thermal value 3R from 2 1/3 R to 2.917 R, which is 2 11/12. So it's 3 minus that initial level. So I'm trying to explain this right. I don't fully grasp this in spite of extreme effort. But that's what I think is going on here. So 2.917 R, and enables the thermal motion to continue on the basis of the preferred negative initial level up to a considerably higher temperature. So this basically means that you can put much more heat into the system and still remain in the time region, still not have to reach that melting point. So it's an expedient for the atom to do it, to remain in the solid state, because the solid state is more probable than moving across that boundary. And that is one of the major principles that Larson deduces his universe from. The universe is always, again, the second postulate, the universe subscribes to mathematics. And so the universe is always going to do what is most probable, or it tends to do what is most probable. And given all other things being equal, it will do the thing that is more probable. And the lower numbers are always more probable than higher numbers. And, less energy configuration is more probable than a higher energy configuration. So that's the principle he's working with here, I believe. And enables the thermal motion to continue on the basis of the preferred negative initial level up to a considerably higher temperature. Okay, so this creates an inflection of the curve that, you know, you can, the slope is now 8 times what it was before. When the rotation 2 curve reaches its endpoint at 2.917, again, the ultimate boundary is 3. So at 2.917, it can move then into the third level, and that would be reducing it by even more, because now you're using the fraction 1/27th instead of 1/8. You know, 1 to the third, 2 to the third, and 3 to the third. 1, then 8, then 27. Okay, so the net at 2.917 are net positive specific heat, a further reduction of the initial level by a transition to rotation 3 basis, where the higher rotation is available, raises the maximum to 2.975 R, which I do not understand where he got 2.975, because I would think it would be 1/27th, which would be something like 2.963. I figured this out at one time, but I don't exactly understand why the maximum would be 2.975, and I wish Larson would show his work here. So, you know, a lot of times he skips these steps. So anyway, I think I'm going to think about this overnight, and maybe I'll have an answer for you tomorrow as to why this specific heat, this maximum is 2.975 right now, because that would be 1/40th. 39 out of 40, or 2.2 plus 39 over 40. I'm not sure, but we'll try to figure it out. Otherwise, we'll just keep moving, and we'll be okay with not understanding it, hoping that we will understand it at a later time. And we will resume again tomorrow. So thanks for tuning in today. Have a great